All right, morning everyone. Welcome to today's a16z crypto research seminar. Justin Thaler from Georgetown is back. He's going to be giving part 2 of his SNARKs tutorial. We'll see if there's a part 3 later or not, but for now, let's hear part 2.
Thanks, Ted. Yeah, so I'm going to start today by recapping the first talk, in case anyone is joining for the first time today. And then I will kind of continue or complete the overview of rollup projects. So last time I sort of described the idea of a rollup, what rollups are trying to accomplish. But today I'll actually kind of dive deeper into the details of what specific projects are doing. And if there's time, I will then tell you a little bit about how these SNARKs actually work in sort of more detail than I described last time. And that's where we'll see if I might or might not have time for that. Okay, so here's the abbreviated recap, kind of 90 minutes into 4. So let me remind you, what is a SNARK? So the prover claims to know some witness satisfying some property. And just as a concrete example, this could be, the prover and verifier might have agreed on some cryptographic hash function and some output y of that hash function, and the prover claims to know a preimage w of that hash function output. So the trivial proof that the prover knows w would be to just send w to the verifier, who can just directly check that w satisfies the claimed property, in this case by evaluating the hash function on w and confirming it spits out y. And basically a SNARK is just any way for the prover to prove to the verifier that it knows w with costs better than that of the trivial proof system. So succinct means that the proof is shorter than actually sending w explicitly to the verifier. And ideally, the proof will be faster to check than the verifier's runtime in the trivial proof system, and in that case, we'll call the SNARK work saving for the verifier. In general, SNARKs are designed in a 2-step process. So there's a front end and a back end. And ideally, the front end will take some computer program written in a high-level language, which takes as input the witness and sort of checks that the witness satisfies the claimed property. And the front end will transform that computer program into an equivalent representation, typically something like a circuit satisfiability instance, because things like circuits are kind of easier for the SNARK proof machinery to be applied to than directly to some high-level computer program. And then the SNARK for circuit satisfiability, so people like to use variants of that in practice or generalizations, that's called the back end of the system. Last time I described the standard paradigm for designing SNARKs. It's a 3-step process. So first you design a protocol called a polynomial IOP, and I said last time what that is, and if we get to the part of the talk where this is relevant again today, I'll of course remind you. The second step is to design a cryptographic primitive called a polynomial commitment scheme, and if you put these two together, you get a succinct interactive argument, and then you can just pull the interaction out to get a static proof, a non-interactive proof, by applying something called the Fiat-Shamir transformation. Okay, so with sort of that background on SNARKs out of the way, here's like the one slide that tells you how a rollup works. So the idea is that sort of without a rollup today, blockchains are sort of storing the entire state of the world on the L1, so on the layer 1, that means on the blockchain. So that means like all of the blockchain nodes kind of have to know like everyone's account balances or something like that. That's what I mean by the state of the world. It's like all the data that lives on the blockchain. And the rollup seeks to avoid that by storing only a commitment to that data on the L1, a cryptographic commitment. So think of this as just like one cryptographic hash value, which somehow binds everyone in the world to the underlying data, but the commitment itself is tiny. It's just like 256 bits or something like that. And the idea of the rollup is that it's going to process a big batch of transactions and figure out what is the new state of the world, by applying that batch of transactions to the current state of the world. Right? And then compute a commitment to that new state and post that new commitment on the L1, on the blockchain. Okay, and the problem with that is we don't want to just trust that the rollup service does all that computation correctly. So we don't want to just trust that the rollup sort of correctly applied all of the transactions to the old state of the world and then correctly computed the, a commitment to the new state of the world. So the rollups will pair the new commitment with a SNARK proof that the new commitment is correct. Right? So that means like the rollup's going to prove that it knows a bunch of transactions such that all the transactions are valid, meaning they come with a digital signature, and none of them involve somebody spending more money than they have in their account, things like that. And the rollup will prove that when you apply those transactions to the old state of the world underlying the old commitment, it leads to a new state of the world underlying the new commitment. And I just want to remind everyone, I had a discussion last time about how you measure the performance of these rollups. And sort of there are two things you might care about, latency and throughput. Latency is determined by two things. So this is the delay between when a transaction posts to the rollup service, which we call layer 2, and when a proof capturing that transaction posts to L1, which is when we consider the transaction to be finalized. So the two contributors to latency are the time to compute the proof, right? Because we kind of have to wait around for that proof to be there before we can post it to L1, obviously. And also we have to wait around for enough transactions to hit the L2 that the rollup is kind of ready to treat them as a batch and roll them all up by computing the relevant proof for them and the commitment that corresponds to the state following their processing and all of that.
So the main reason you want like a lower bound on batch size is just so that the amortized cost per transaction is low enough, or?
Yes. Exactly. So if you had
something like gas cost, like L1.
Yeah, this is all about saving gas on the L1. Of course, there are gas costs there because blockchain nodes have to do work for every transaction and store state for every transaction. So you make people pay for that because otherwise, people are just going to try to get as much transaction data as they can on the chain, and the nodes will all fall over. So this is all about saving gas. That's why you want the batch sizes to be big. And there are sort of, I guess you could say, there might be economies of scale to bigger batches. So it's not just that more batches are getting kind of cryptographically compressed into a single commitment and proof, but it's also that the proofs involve like if multiple transactions in a batch refer to the same account, you kind of get multiple reads to the same piece of data. So the prover is only having to deal with authentication information for that piece of data sort of once. It doesn't have to pay every time. And often, we're going to talk about data availability again in a minute, but a lot of rollups are storing the data underlying the commitments on chain, and you sort of only have to store sort of the latest account balance on chain in principle, right? So if in a single batch, like 18 different transactions hit the same account, you can kind of net them all and only pay to store the final result on chain. You don't have to store 18 different values. So there are kind of multiple ways that big batches help save the costs of a rollup.
I don't know if this is interesting or not, but I noticed that you define latency as like the moment that you hit L1, you assume that, are you basically abstracting like that L1 is kind of perfect and instantly final in this case? Like I wonder if there's interactions between the fact that posting to L1 for some types of blockchains doesn't really guarantee that the thing's finalized, because like that
Of reorganization.
Yeah, L1 could reorg, yeah.
Yeah, so I mean, I guess the simplest thing is to wait long enough, if it's proof of work chain, wait for enough more transactions. I guess that also applies to proof of stake. That is just considered final on L1. And that's what I mean by post to L1. But there are other subtleties I'm about to raise when we talk about data availability, which is I was seeing that some of these rollups have ways to revert state if bad things happen. Well, okay, I don't know details about if they've at least discussed the possibility of reverting state even after proofs might have posted to L1. So you might have to be very careful about what you consider finality if something like that might happen. But yeah, at sort of the crudest level at least, people sort of consider the rollup to the transaction to be finalized when a proof that kind of incorporates that transaction hits L1, whatever that means.
Yeah, and basically it's confirmed on L1.
Yeah, confirmed on L1. Yeah. Yeah, I guess if it's possible that L1 might sort of drop the block that has the proof in it, then there's no sort of global record that of the proof anymore.
I guess the question we should come back to later is like, is every rollup design suffer from this problem equally, or some like more tolerant of reorg or something being dropped?
Yeah. Yeah, we should discuss and think about that. It doesn't seem particularly specific to any rollup design. Just the whole notion of a rollup posting a proof capturing a basket transaction seems to be key. But definitely, their plans to sort of deal with possible attacks definitely factor into finality, and I'll discuss possible attacks momentarily. Okay, so people obviously care about latency. Yeah, this also means, by the way, if if your transaction that's in a batch is a withdrawal transaction, I think you don't actually get your money back on chain until a proof capturing that withdrawal transaction hits the chain. So in that situation, even if the rollup service provider or some intermediary, you're an end user and there's some service that's using the rollup provider, even if they're willing to kind of grant their users finality before the proof hits the chain, if you're trying to withdraw from the rollup, I think you just cannot actually, get those funds kind of liquid in your wallet until that the proof capturing the withdrawal hits the chain. So yeah, you can. As with optimistic rollups, I think people can kind of step in and potentially, provide liquidity before finality, kind of take on risk, if you will, so that end users don't have to. But I don't know. Yeah, but if you're trying to do like a direct withdrawal from a rollup, I think this latency is really going to matter.
Because I think it's usually like two transactions, right? Because you need a withdrawal transaction within the rollup. And then you submit your own that comes from the rollup server, and then you submit your own thing to actually move them.
Yeah, to pull the funds from the rollups.
From the smart contract.
Yeah, smart contract of the rollup to your wallet. Yeah, I think that's how it works. Okay, so that's latency, and then the other measure of performance is throughput. So this is the number of L2 transactions that can be processed by the rollup in a given amount of time, and we had a fairly lengthy discussion last time about how, due to something called pipelining, this actually has nothing to do with latency in principle. So maybe I'll summarize that in a sentence here, just as a reminder for those who weren't here last time. So the idea is, imagine it takes a year to compute a proof, okay, but the proofs are really small. So once you have a proof in hand, you can get it on L1 really quickly. And sort of in steady state, you can do this thing where you're actually getting a proof onto L1, if it only takes a minute to upload a proof to L1 once the proof is in hand, you can actually get a proof onto L1 once per minute in steady state. It's just those proofs are kind of capturing year-old data. So you think of as soon as you have a batch of transactions kind of ready to be proved, you hand it off to the prover, you kind of think of putting it in a pipeline that takes a year to get through the pipeline. Right? But after that initial year is done, then every minute you're kind of throwing a new batch of transactions off to the prover, and a proof is coming out the other end of the pipeline, and you can throw that proof up onto L1, and this just happens every minute. A new batch goes to the prover, a new proof comes out of the pipeline, you throw it up on L1. So in principle, this has nothing to do with latency, but of course, in practice, people won't tolerate 1 year latency. yeah, like to maximize throughput, you kind of want your batch size to just be as big as it can possibly be, because that gets the most kind of savings or compression of the transactions, since these SNARKs have succinct proofs that grow sublinearly with the statement being proved. But there's limits put in place by latency demands, but also some of these SNARKs, like the provers, will just kind of fall over when the statements get too big. So there's lots of things that sort of can limit throughput in practice. But yeah, I sort of flagged this last time because a lot of the rollup projects will discuss performance in terms of throughput, like transactions per second. And if you sort of don't know that that they're talking about latency, you might think like transactions per second is referring to like the speed of the prover, like kind of the end-to-end pipeline, which would be really latency, and that's not what they're talking about. And that makes sense because throughput is ultimately what determines blockchain scalability in terms of just like how many transactions the blockchain as a whole can process in a given amount of time. But it's just, yeah, you have to know what people are talking about. If you don't have the context, it can be very confusing. Okay, so I guess I will mention, this is the last thing I talked about last time. A bunch of rollups today are doing recursive proof aggregation or composition. And this, I guess covering this also clarifies the pipelining thing. So the idea is they want to sort of work on smaller blocks than they otherwise would. But they can work on the small blocks in parallel. So the idea is you process like a small block, compute the new commitment, and send the little small batch off to the prover to start chewing on the proof. But as soon as you know this commitment, you can kind of start processing the next small block and send the next that small block off to the prover to compute the next proof. And you can do that before the first proof is finished. So you can sort of do everything in parallel, and then this is effectively reducing your batch size. So now you have one proof for each small batch, but you don't want to post all of those proofs to L1 because your gas cost savings will be poor. So what you'll do is you'll sort of recursively apply the SNARK to aggregate all of these proofs into one small proof. The idea is you'll use the SNARK for the prover to prove that it knows the proofs pi1, pi2 up to pi t that would have caused, each of which would have caused the verifier to accept. Okay, so you need to take the SNARK verifier for the small batches, like represented as a circuit or something, t times, once for each batch, and then the prover gets applied to that circuit to prove that it knows these t proofs that would have convinced the verifier to accept. Okay, does that make sense?
So the witness at the top level is just the pi i's, right?
Yeah, and it's the pi i's, and I guess also the CIs, because the on-chain verifier for the if you were posting these on chains also needs to know the commitment to verify the proof.
Gotcha. And then at the bottom level, it's sort of subblock 2. You kind of, the point is to verify the computation assuming some given initial state at the beginning of subblock 2.
Yes.
Right, and then the correctness of that will be verified in the first of the subblocks, right?
Exactly. So this proof is ultimately going to refer to this commitment. Because if you imagined you weren't doing this recursion, you were just posting these proofs online, like the on-chain verifier would have needed to know this commitment to check, like the statement being proved involves this commitment. So that's why you do have to know C1 before you can start dealing with subblock 2, or at least proving subblock 2, working on computing pi 2.
Right. So in effect, there's like a state checkpoint in each of those subblocks, right?
Yeah, exactly. And the reason to do this is kind of twofold. So the provers in like most SNARKs can be parallelized, but it can be a bit hairy. Many of them require the prover to do a giant FFT, and that can be parallelized, but there are certain limitations on it. So this is unlocking more in sort of trivial parallelism, because like almost trivially, like as soon as you know C1, you can just start in parallel working on computing C2 and Pi 2. And the other thing is, I had mentioned when these SNARKs get applied to really, really big statements, the prover can often just fall over. Some of them are very space intensive for the prover. So this is ensuring that some of the nastiness of the prover, like you don't run into because it's only getting applied to smaller statements, but then you're still getting sort of the gas savings as if it was applied to a big statement, since you're aggregating the proofs rather than posting each proof onto L1. Okay, so I wanted to review that because so like ZK Sync, one of the rollup projects, has been doing this for a long time. Actually, as I mentioned last time, they originally were doing it because they were working with a structured reference string that was too small to handle very big statements. But then other rollups that use different SNARKs are just now sort of launching this kind of recursively composed situation. So I will be discussing some of that later. And then, yeah, the last thing I wanted to discuss before kind of going to new material is data availability. So because on the L1, we might only be storing commitments to the underlying data that used to live on the blockchain. You have this issue of, well, where is that data going to live now that used to, the data underlying the commitment? And the reason we need it to live somewhere and be made available to people is, I guess, twofold. So one is like the rollup provider might just disappear one day or be compromised, and someone else might want to step in and take over. Or if someone might be like getting censored, like the rollup provider is refusing to include their transactions in the batches, and then they have to like force withdrawal of their funds. And I think you can't do that if you don't know the state underlying the commitment. So yeah, it is important to have the data be available, and if it's not just living on chain, then how is it going to be available? And sort of there are two different approaches out there. One is to kind of store it on chain anyway, but it can sort of be semi-on chain in a much cheaper way. So in Ethereum, there's something called call data, and that's where this data that sort of used to be like subject to the kind of full consensus mechanism of Ethereum and stored by like all the nodes, now can live in sort of this cheaper call data that's not stored by all of the nodes verifying the blockchain. And then there are approaches that will kind of keep the data off the L1 and use economic incentives to try to get other parties to make it available. So I wanted to just have a slightly longer discussion about data availability. Yeah, sure.
So, thinking about your examples about why you want this call data, I mean, I think fundamentally what you need is just the ability to reconstruct the full state of the virtual machine, right? Mm-hmm. And one way you can do that is re-execution of all the transactions.
Right.
So I would say, like, having a list of all transactions is sort of sufficient for state reconstruction. It's not obvious it's necessary.
Right.
There's some other way you can communicate it.
Right.
Is that right? Is it right that we only care about the transactions in as much as we care about state reconstruction?
That's correct, yeah. So, I mean, basically, like to withdraw your funds assuming that the rollup has provided like a forced withdrawal mechanism, which I think they're all doing, otherwise people maybe wouldn't use them because they'd be worried their funds would get censored and then they can't get them out. I think what you would need to know is like your own account balance, which maybe you can just track yourself, but then you also need to know the authentication information to prove that it's consistent with the latest commitment that's on chain. And that sort of involves like aggregated information potentially from all account balances in the whole world. So you definitely don't need to know like the whole list of transactions that led to the latest state of the world, but you do need to know, if not the full state of the world, like enough to get that authentication information, which in general, in the worst case, is like the full state of the world, basically.
So the ZK proof can only give a commitment to the state of the world, right? When the rollup.
Yeah. So these proofs that are getting stored on chain, so there's the commitment, and then there's a proof that the commitment like was computed by applying valid transactions to the state of the world underneath the old commitment. So this data that I'm talking about making available sort of has nothing to do with the proof.
No, I'm saying, so it gives a commitment to the new state.
Mm-hmm.
And is there any way to update the state that's, suppose the state is stored on chain?
Mm-hmm.
Can you update it with the commitment and prove that?
Yeah, so this is going to get into, so let me jump to the discussion. When you say you, do you mean like you're not the rollup provider, but you're someone who knows the state of the world? Can you now like update, can you function as a rollup provider? So that is the perfect segue to this little conversation I wanted to have, which is, should entities other than the rollup service be able to submit proofs to advance the state of the system? Okay, does anyone have any thoughts on that? So Joe's giving a thumbs down. Do you?
I mean, if you know the old state and the commitment, anyone no, what if the rollup provider themselves update the proof every time they add a new proof? Update the state every time they add a new proof.
Like on chain?
Yeah.
So-
They give a commitment to it, and then they can also change the state and then prove that it is consistent with the commitment.
Yeah, so that's basically what they're doing now. If they are keeping the state of the world on chain and call data, that is what they're doing. So with every time they update the commitment, they also include, they have a bunch of call data that they include too, and they pay the gas fees to get that stored, in the on-chain call data. People call this like semi-on-chain, I don't know, because only full nodes are storing it or something. So that's what they are doing now, but there's more and more services that either have or are soon planning to roll out off-chain data storage, and then they might no longer do that. Yeah, I mean, if you just like trust the rollup service in every way, you can obviously just trust them to solve data availability themselves, right? But the whole point of being worried about data being available is, what if the rollup service gets compromised? What if they're trying to censor you, and you have to force withdrawal from them?
Yeah, but if the other case is the rollup service goes offline or something.
Yeah.
But then the final state is on the actual blockchain, right?
If a commitment to the state is on the blockchain, and if they're using like the sort of call data based data availability solution, then also the underlying data is on chain and at least living in the full nodes or whatever. But again, there's this big push to not do that, because the gas savings of rollups is sort of bounded, and what I read is bounded by about 100x or so, if you're sort of going this call data route. And maybe some of the upcoming EIPs, if they get approved, sharding, making call data expire after a year, things like that, maybe that, I don't know if that moves the 100x up a little bit. But when people will talk about, like 20,000x improvements, and I think you really need data off chain if you hope to do that. Even if they incorporate all the EIPs that are being proposed. And again, that refers to throughput. Okay, so Joe, did you want to advocate?
Yeah, I actually think it's pretty interesting. I think there's kind of arguments in both ways. I think like the philosophically correct answer is that anyone should be able to submit a proof. It's like the proof is self-validating, but it seems like it opens things up to a lot more potential attacks and risks. So it's not obvious that it's actually the right trade-off.
Mm-hmm. Yeah, so I think I don't think there is a right answer, but I guess just to clarify, I guess if you did want only the rollup service to be able to submit proofs, you could do it just by requiring them to sign the proofs, right? The smart contract says I look for a digital signature of the corresponding to the rollup service's public key or something. So if the answer is that only the rollup server should be able to post proofs, I guess the concerns then are like centralization and censorship. Right, like the government, maybe someone could go to the rollup service and say, do not process transactions from this public key, they're evil, they're an evil party, don't do it. And then I guess that party should hopefully be able to force a withdrawal, but they can't use the service anyway. And so if the world is run by a handful of rollup services, maybe, I don't know, maybe that party has to pay crazy gas fees that only rollup providers that have taken over the world can pay, or, because they can't use a rollup service, who knows? So I guess those are the concerns. How can you say that the blockchain is decentralized if the rollup services are centralized and are running the world. I don't know.
I mean, there's also like there's kind of a disaster scenario if you make them sign every update that they lose that key.
Yeah, that too.
And there's no progress again forever, but you could probably hedge against that by saying like if the rollup server doesn't submit an update for X blocks, then like all of a sudden it doesn't need to be signed anymore. You kind of open it up, or you have like a backup key or something.
Yeah. There seems a really big design space here. But if the answer is yes, and anyone can submit a proof, or if the service gets compromised, I did want to discuss the following data availability attack, because actually this hadn't occurred to me until I was making the slides for today. So I guess these things are nice to raise. And then I found discussion online. The rollup services are thinking about exactly this kind of attack and what to do. A party, whether the person who sort of now has taken over the rollup service or the person, anyone out there who's allowed to function as the prover, can honestly generate a proof that processes some legitimate transactions, but then they just don't tell anyone in the world what the transactions are, or they put out fake transactions that don't actually correspond to the proof. If you're not careful and are not checking for that, they could try that. And the point now is that the system has been sort of updated on chain. There's a commitment now to an updated state of the world, but no one but the attacker knows the new state of the world. So the whole rollup is bricked. No one else can advance the state of the world. Because to do so, you have to know a bunch of authentication information, and even a single transaction is going to affect authentication information for the whole state of the any piece of data. Yeah, does that make sense?
It seems like there's a lot of different ways that these could potentially get bricked. It would be interesting. As far as I know, it never happened, but it'll be interesting to see in the next year or something if the first rollup server actually somehow manages to get itself stuck.
Yeah.
On this slide, there's 3 different ways they can kind of get stuck forever.
Right. And obviously, I'm just raising this as something that everyone has to think about, and I'm sure the services are. Now I'm going to tell you a solution to prevent this attack, even if anyone in the world can update the proof. But this is not necessarily the solution that the services are using. I actually don't know in detail what they're doing. So here it is. So if the data is being stored on chain, the state of the world is in this call data, you can demand that the verifier, so the smart contract that runs the SNARK Verifier, demands all state changes as call data. So it will take as part of its input the latest state of the world written to the call data. Okay, and it will then have to sort of treat that as what's called public input to the circuit that it's applying a SNARK to. Right, because as I described how rollups work previously, the prover is going to prove that it knows a bunch of transactions, and the new state of the world that kind of follows by processing those transactions, applying them to the old state of the world, and then show that the new state of the world kind of underlies the new commitment that it's posting to the chain. And in that situation, the new state of the world is part of the witness that the prover knows but is never revealed to the verifier. So what I'm saying is you have to get that part of the witness out of the witness and directly into the verifier's hands. So you could think of it as still part of the witness, but it's getting sent explicitly to the verifier. But it has to come directly from the on-chain storage now, right? Because the verifier is basically trying to confirm that the new state of the world is actually on-chain, so it's available to everyone. And so done naively, this is extremely expensive because the way that many of these SNARKs work, any public input that's fed to the SNARK Verifier, each little piece of data that's part of that public input, you have to do cryptographic operations. The verifier has to do cryptographic operations for. So this is substantially increasing the size of the public input to the SNARK Verifier, causing the SNARK Verifier to do a whole bunch of crypto operations, therefore greatly increasing the gas costs of running the rollup verifier on chain. But there's fortunately a technical trick you can do to alleviate this called the hash trick. So this is cryptography's hash trick, not like machine learning's hash trick. So what you do is rather than having the whole call data be public input to the verifier, public input means like both the verifier and the prover know it. You only make a hash of the call data available to the verifier. And the verifier is just going to check directly, and this is really important, outside of the SNARK proving machinery, that this claimed hash actually is the hash of some call data. So outside of the proof machinery, the verifier is going to take a bunch of call data, compute its hash, like SHA-3 of call data, and confirm it equals like this public input being fed to the SNARK verifier. Right? I'm distinguishing here between like the smart contract verifier and the SNARK verifier, which is probably confusing, but basically the SNARK verifier has to do a whole bunch of crypto operations for any public input that's kind of getting fed through the proof machinery, and here we're making sure that only the hash is getting fed through the proof machinery. Whereas the smart contract that is doing the rollup verification is sort of free to also do other checks that don't involve the SNARK at all. Okay, so it looks like this is not coming across totally well, but maybe a hint of what's going on here is coming across. Yeah.
So, just to make sure I understand, the only advantage of this over, like, why do we even need rollups? Is because you store these things semi-on-chain. If it was not called data but just on-chain, then there's no advantage to rollup here, right? But why do you do all the rollup is to save putting it on-chain. So now you're doing it semi-on-chain.
So that's
I think there would still be an advantage though, because you don't have to put all the signatures on chain. Right? You just need to know like A paid B, but the signature or any other data that validates that can all be like a witness to the SNARK.
And in principle also, like what needs to be available on chain at any time is kind of the latest state of the world. You don't need to know the whole history of transactions that led to that. So I don't know that people are doing this now, but you could sort of forget transactions on chain and just at all times only have the node storing like kind of the latest state of the world. I'm not saying that this is an easy thing to engineer or that anyone's doing this. I'm just saying in principle.
Wait, but in this solution you need all state changes stored on the call data.
In the call data, what you need is the current state of the current data underlying the current commitment.
Oh, okay, yeah. You're saying you would forget.
So you could forget everything else. And I don't, Joe, do you want to say?
Hold on. I mean, you can't represent that as like the full state of the world in call data in each block, right? That would be like way too big. It's only the changes, right?
Yeah.
Yeah.
Well, so. Okay, so I guess if I'm understanding what you're saying correctly, you're saying that something that people actually, I guess, do now is they're storing only sort of deltas, like differences between each state update. So they are remembering kind of the whole history then, in a sense, but like any kind of, they can net out multiple transactions within each batch, within each state update, right? So if like in a single batch, there's 1,000 transactions that all, 500 of them increased in account balance, 500 of them decreased in account balance, they can all sort of net out and you don't need to know the individual ones, which is, I guess, related to what I was saying, but
Yes,
not the same.
basically, if you put every effectively you have to put every transaction, like a summary of every transaction in the call data, but you save on, I guess, netting, because you can net transactions, and then you save on all the witnesses, like the transaction witnesses' signatures, which don't have to go on chain.
In worst case, this is as costly as the transaction. If every transaction operates on different states, different parts of the state.
Well,
Yeah.
You still save
One
the
of the
signatures.
Right.
But that's usually the signature is bigger than the effect of the transaction.
And you're also saving like the time of all of the blockchain nodes verifying every signature. So it's you get to both cut out the storage of the signatures and the time to check their
So
validity.
half the space and all the verification.
Yeah, something like that. Yeah. Okay. Yeah. So that's the savings if you're keeping stuff on semi on chain. with off-chain storage, which is like really where the giant gas savings will come in if people sort of are comfortable with this, here's something else you could do. So you could have some like just other distributed systems, say using BFT techniques to achieve consensus or something. And that other system can like threshold sign the hash value that's supposed to be the hash of the new state of the world. Basically attesting that that they are storing the state of the world. So the idea is like if enough people have said, okay, I'm going to try to make this data available, the L1 is going to say, okay, well, I guess I'm convinced that this data is going to be made available because enough of you have said that you downloaded it, that someone should be making it available. So this is basically reducing, it's a reduction from the liveness of the rollup, from like data availability for the rollup, to sort of liveness of the BFT system, that has now sort of attested with some kind of majority or 2/3 or something that BFT system is going to make this data available. So it's just kind of placing the trust in the BFT system instead of in the costlier solution that was keeping the data sort of semi-on-chain. And just as a reminder, like the nice thing about cryptographic commitments is that nobody can like futz with the data and change it. So like you only need really one party to be able to broadcast to the world what the data is that they're supposed to be making available. They don't need to. There's no way that someone can maliciously like change that data because they wouldn't be able to authenticate it with respect to the commitment that is stored on L1.
Yeah, I was going to say, like, I don't think you need a BFT system for this. I think it's much simpler because you only need one party to keep the data, and they don't really need to reach consensus because if you believe like the L1 achieves BFT or achieves consensus, then they can all just check that they're storing. They can check if they got the right data by checking the commitment that's on whatever the main L1 chain is.
Right. Yeah. So I guess the concern would be that it'd be expensive if you got 1 million people saying I have the data, I have the data, I have the data, and you sort of have to figure out which one is telling the truth. Like you can check, but you have to potentially check a whole bunch of people if there's malicious parties out there, and that's just expensive, I guess. You don't think that's something people are concerned about?
I mean, I guess you could sort of do it through some like smart contract where people claim they have the data and don't, and they like pay some.
Yeah, they pay some. Yeah.
Yeah, I don't know. Yeah, it seems though like you could have some simpler like kind of just I don't know, like you have X nodes and they all say they have the data, and as long as one of them is honest, then you're kind of okay, right?
Right. Yeah. So at any rate, like. Yeah, basically, if enough people say they're going to make the data available, you only have to trust one of them. So it's probably fine. And basically, if 50 people say they're going to make it available, one of them is going to.
And I guess BFT wouldn't actually even help with the attack that you're talking about, because if you have a BFT system, you can still have like malicious nodes that will lie about having the real data, so you still have to check, right? Like anybody who gives you the data, you still have to check.
Yeah, I guess. Yeah, I don't know how big the threshold here would be for the threshold signature. Like if it's above a majority, then you could just Anyway, this is, I just mostly wanted people to think about this data availability problem in more detail because I was just thinking about it almost for the first time as I was preparing this talk and realizing the subtleties and thought it was a useful conversation to have. So I did it online in the talk. But yeah, thanks so much, Joe, for keeping me from saying anything too dumb. Any questions at this point?
So effectively, there's like no solution to data availability.
I mean, I know what some of the projects are planning. You have. Like ZK Sync is planning something called ZK Porter. They're going to, I believe they're launching a token and using basically proof of stake to try to incentivize people to make data available and also sort of be honest about it so people don't waste their time, I guess, checking it and it turns out not to be correct.
It sounds like a second blockchain to make it.
Potentially, and it's just, you just have this nice property that no one can futz with the data, but you know, there is, I guess, potentially a cost if people do want to try, there's a cost to sort of root them out, I guess. I think Starkware is already keeping data off chain, but I don't know exactly how they are dealing with these issues. I don't know the details. There's a large design space. I mean, people have plans at a minimum if they haven't launched, and I guess it remains to be seen how some of these play out, I suppose. Yeah, it can be hard to follow like where some of these projects are with their plans, and you know they've been openly discussing their plans for a while, and so you find an old post and it's hard to figure out like, well, has it been implemented yet or not? Yeah, it's just there's a lot of activity in the space. It's hard to track. You know what was planned. You know, very open discussions about plans and what's actually been done. Okay, so I guess we'll dive into what the rollup projects are actually doing, especially in terms of their SNARKs, because that's what I'm an expert on. And there won't be too much discussion about data availability anymore. Okay, so remember, SNARKs kind of work in a two-step process. You got this front end, and that sort of spits out some kind of circuit satisfiability instance, and then you apply a SNARK for circuit satisfiability instance. So let me start with front ends. Okay, so there's sort of two extremes that are very prominent, at least. They're maybe not the only approaches, but they're certainly, I think, the most prominent ones being pursued. So one extreme is kind of inhabited by Starkware, which has exposed a high-ish level language. One bullet point later, I'll call it a limited assembly-like language. So it's it's higher than just writing down a circuit for sure, but it's still a somewhat low-level language, not like Java or something. Anyway, so a high-level language called Cairo to programmers, and they have an automatic compiler that turns Cairo programs into circuits. So the language, sort of the programmer has to be aware of many SNARK-specific issues, and there are limitations to it. So for example, like all arithmetic in Cairo is done modulo a large prime, and greater than and less than, like integer inequality tests are not supported. And I believe the programmer has to actually, leverage what's called non-deterministic advice, which is kind of taking advantage of the ability that you're dealing with a circuit satisfiability instance and not a circuit evaluation instance. So there are sort of ways to keep the circuit small by sort of adding extra elements to the witness called advice. And I believe the programmer in Cairo sort of has to explicitly program that advice in many cases. I think that's true, just looking through their high-level descriptions of Cairo without actually using it myself. Yeah, so the idea here is you're sort of pushing more responsibility to the programmers and giving them like limited expressivity. I guess programmers today write smart contracts in Solidity, and for a ideal programmer experience, you'd like them to not have to change that. So that's the other extreme, is just let programmers write in Solidity, and there are a whole bunch of projects seeking to do this, and they sort of all use the term ZK EVM, but mean slightly different things by this. Ultimately, the circuits that they're planning to use might differ. I think some of them are, okay, so last time I mentioned, so I'll say this again, I believe the way Ethereum smart contracts work is they're typically written in Solidity, and then they're compiled into what's called EVM bytecode, that's Ethereum virtual machine. And then the smart contracts actually execute that bytecode. So I believe some of these projects are like literally kind of taking each bytecode instruction and coming up with an optimized sort of circuit that implements that bytecode instruction. And so they're working sort of directly with representing the bytecode. And others are kind of transpiling Solidity into like other lower level languages and then sort of turning those other, so they're not going through EVM bytecode. and then turning those other lower level languages into circuits. So just different sort of engineering approaches to go from Solidity into the circuits that are equivalent to the Solidity program. And as far as I know, I've heard the Starkware team like publicly, like podcasts say, like one reason they chose their approach was basically faster development time. Like they could, like this just takes a ton of engineering to make this reasonable. So they went with like the kind of easier compilation problem where the language is sort of designed so that all programs in it are SNARK friendly and amenable to like kind of standard off-the-shelf techniques. So I believe, as far as as I understand, the ZK EVM projects have not yet launched full front-ends and back-ends on testnet. So like I think ZK Sync, they launched a testnet back in February. I believe that it's generating and executing circuits, but not generating the proofs for the circuits yet. In contrast, so ZK Sync 1.0, which I'll talk more about in a bit, only supports like token transfers and NFTs. So much more limited functionality than like general smart contracts, but that has been live on mainnet for a couple years already. So ZK Sync 2.0 is what's going to have this very exciting support for Solidity, where no one will have to know anything about SNARKs to use it, but it's a very difficult engineering problem. Okay, any questions about that? Yeah.
So does a prover need to know the front-end circuit when they are checking a proof?
Yeah, they need to know the circuit.
Especially on the verifier, on-chain.
Yeah, so great question. The verifier needs to know the circuit too, because if it doesn't know the circuit, it doesn't know what the prover is actually proving a statement about. And I'll say more about this shortly. Okay, so something I want to point out is that there might be a tension here between achieving performance of these rollup projects and security, in the sense that especially with the ZK EVM projects, because it's just a very difficult problem to turn general Solidity programs into circuits. Solidity was not designed with SNARK proving machinery in mind at all. So what many of them are doing is they're sort of using very intricate hand-coded gadgets, which just really means optimized circuits for common subroutines or instructions. Okay, so just as an example to give you a sense of this, ZK Sync 1.0 in the ZK Sync repo, so this is not even dealing with ZK EVM, this is just NFTs and transfers and swaps. They have 5,000 lines of Bellman in the ZK Sync repo. So Bellman is a language, you're almost hand coding a circuit, just writing down gate by gate the circuit almost. It was originally designed for Zcash, I think, and now the whole community uses it. But then even outside the ZK Sync repo, they have something called the Franklin Crypto Gadget Library, and that has well over 5,000 more lines of Bellman in it. And something that's particularly complicated just for them is, I think I mentioned that they're doing this composition of SNARKs, and it's kind of nasty to represent a Snark Verifier as a circuit. Exactly what complications come up depends on what SNARK you're using, because the verification machinery is different. So they wound up with an annoying situation where Ethereum today supports just one pairing-friendly curve. People have different names for it, but BN256 is one of the names. And for technical reasons, this curve is not friendly to recursion, to representing the Snark Verifier as a circuit. So they wind up having to implement really, really, really big integer arithmetic in a finite field in a circuit. And so one of their big, and so achieving this when they did in 2020 is a huge engineering accomplishment. But it's complicated to make that efficient. The circuit's really reasonably small. So that's 5,000 or 7,000 lines of Bellman code, just in one repo to handle big integer arithmetic. So just to be clear, I mean, these efforts are some of the most innovative, important engineering efforts in the space. But the tagline of ZK Sync is rely on math, not validators. This is sort of to differentiate from optimistic rollups, where you're hoping that people will raise an alarm if they detect any fraud. They call those validators. But just to be clear, the math might include 15,000 lines of hand-coded circuits. And so, you know, if there is some bug in there, you know, the prover winds up proving a statement about a circuit that is not actually equivalent to the statement that, you know, we really want to be proven. And, you know, maybe that is a security vulnerability, maybe it's just a bug, but, you know, people should be aware of that. So I think formal verification of these circuits is an important direction, like sort of in the long run. It's just, you know, that such intricate hand-coded circuits, you know, auditing, you know, we're going to audit them as best we can, obviously, but it'd be much nicer to have some kind of automated formal guarantee of equivalence or something like that. But it seems like a challenging verification problem. Now, I guess the main project maybe that's not doing this sort of complicated hand-coded circuit specifications is this Cairo compiler. But that's also pushing more responsibility onto programmers. So, you know, it's not clear that that's less bug prone. It's just the bugs might be coming from the programmers who aren't necessarily expert on SNARKs or something like that. And so I do want to mention, so there was a nice paper I learned about recently. So their transformation from Cairo programs to circuits, they formally verified it with some proof assistant. You know, but of course they haven't, I shouldn't say of course, at least right now, I don't believe there's machinery for the programmer to confirm that the Cairo program they wrote matches what they intended it to mean. Yeah, so kind of might be a pick your poison situation, just to be aware of. Okay, the last thing I want to say about front ends. So Cairo picked an interesting approach to generate their circuit. I was surprised to learn this actually recently. So they generate a universal circuit with a von Neumann architecture. So that means it actually takes as public input the Cairo program to be run. And like the circuit itself kind of compiles and runs the program on the witness. So I think this gets to your question. You know, you don't want to have so the smart contract SNARK Verifier needs to know the circuit that you're dealing with. This is one way to deal with that and to have just one smart contract that supports all circuits, is to just have a universal circuit like this. But this is sort of well known to this approach to generally lead to big circuits. It's analogous to like a CPU architecture, in particular a von Neumann one that's kind of compiling the program as part of the computation, versus an ASIC. An ASIC is like an application-specific circuit. And there's sort of two main sources of overhead here. One is the circuit winds up repeating like the entire transition function of a CPU for every step of the program. And so it's like, you know, at each step of the program, like only one of the possible CPU instructions gets executed, but the whole transition function sort of has to have logic. It doesn't know in advance what that instruction is going to be. It has to have logic kind of implementing all of them. And that's another reason I think they probably try to keep the Cairo language as limited as possible to keep that transition function as simple as possible. So hopefully I'm giving some sense of what this means. Like an ASIC, if you somehow know in advance or something, what instruction is going to get executed at time step 50, you can just sort of have logic for that instruction there. But if you have a von Neumann architecture, you don't know that, because you have to be able to handle any program. So the other issue is potentially like the program kind of has to get compiled inside the circuit. So you know, I found the blog post Starkware was saying that you know, basically the second source of overhead is not so big, and my guess is that's probably because their programs, they might be fairly simple, but at a minimum they're probably applying them on a very large batch of transactions. So like the work to compile the program might be minimal compared to the, you know, much longer work to sort of run the program on many transactions. But that sort of doesn't address overhead one, because the circuits that they use something called AIR, algebraic intermediate representation, kind of have a CPU formalism built in, right? So whether they're sort of taking an ASIC approach or a program-specific approach or not, they still have the CPU formalism there. So Yeah, I can't say, like, oh, I took a Cairo program and I sort of implemented it with a totally different intermediate representation that takes an ASIC approach, and, like this was the difference in size, but it's sort of well known that there are overheads to this particular approach in terms of the size of the circuits that come out. I do want to mention that the cost of large circuits in these SNARKs is mostly borne by the prover, right? Because verification, tends to, the cost grow very, very slowly with circuit size. So as far as like gas costs, this isn't such a concern. As far as latency and prover costs, maybe it is. Anyway, so this is just my general impression of the approach. And there are other ways to achieve kind of one smart contract for all programs. Like the ASIC approach is still consistent with not having a different smart contract to verify every different smart contract or program people want to write. It's just there are various ways to kind of pre-process the circuit so that the verifier kind of just has to deal with what comes out of the pre-processing. So the pre-processing might be fairly expensive, but it doesn't have to happen like on-chain, essentially. Yeah, so that's what I wanted to say about front ends and how people are taking quite different approaches to the problems.
Do you know how big this circuit is?
I don't. It's probably something that could be figured out, although.
So every instruction in the Cairo language has to be converted to a circuit form.
Yeah. Yeah, but I mean, there's nothing specific to Cairo about that. Like SNARKs just need circuits, and I'm using circuit in a broad sense. That StarkWare itself might think of this algebraic intermediate representation as like not a circuit, but conceptually it is just a certain kind of low-level representation that's amenable to designing a SNARK for. But the specific way they're going about it is, in designing the programming language called Cairo, it effectively involves programming a very simple processor. And they are taking that processor and representing it kind of as something like an arithmetic circuit that operates over a finite field. And then if someone wants to run a Cairo program for 1,000,000 steps, they're sort of repeating that that circuit implementation of the processor like 1,000,000 times. Does that make sense?
So it depends on the size of the program itself, the runtime of the program.
Yeah. So you would say the circuit they finally generate is like, here's the Cairo program, I guess, as public input.
They rolled out as one, for each step there's a different
No, I think this might be more in the details for me to say definitively, but no, I think it's like literally like maybe like here's the text of the program, maybe transpiled in some way. And also the number of steps it needs to be run for or something. And then there's going to be a bunch of advice inputs basically, plus the witness itself. And then the circuit will basically, using the advice, help confirm that. So the advice might actually be like a transcript, like a step-by-step record of running the program for 1,000,000 steps on the witness. And the circuit just checks that like at each step of this transcript, like the transition function or the circuit representation of the transition function of the Cairo program was like correctly applied. That makes sense?
That makes sense. It's kind of almost like an IPC though.
Yeah. I mean, exactly. When IVC is a certain kind of proof system that supports like applying some kind of simple function to an input and proving you did it correctly, and then updating the proof to capture like another application of that function, and then updating the proof to capture another. It's just
the function is the processor right now.
Yeah. But they're not going through IVC. They're representing the many applications of the function as a big circuit and hitting the whole circuit with a monolithic SNARK until they start recursively composing SNARKs, as I sort of had the little two-level tree before, which starts to get closer and closer to IVC when you do recursive composition of SNARKs.
So we're like ZK Sync and other things that aren't SNARK were doing the second thing you said about pre-processing?
So ZK Sync uses Planck, and Planck has holography, fancy term for this pre-processing, baked into it. So, you know, at least at a high level, that's what they're doing. So basically, and it's easy, especially for ZK Sync 1.0, I think, because you know, there's basically only, you know, like 6 programs that might be run, and each is just like swap, you know, mint NFT or something. But like, yeah, for each of those, there's a circuit. The circuit is maybe hand-coded and very complicated, but it sort of gets summarized. So what happens is, what this really means is, there's certain polynomials that capture the wiring of the circuit that's used inside the SNARK. And if I give a third talk, you'll see them. And so you basically, the pre-processing winds up producing cryptographic sort of commitments to those polynomials. So the verifier only needs to know the commitment to the polynomial, you know, so these polynomials like encode the circuit wiring. So the verifier only needs to know sort of commitments to the circuit instead of like a full description of the circuit, which would be very complicated and large potentially. Does that make sense?
Yeah.
And in that way, you can write sort of one verifier that sort of takes as, it has to be like a trusted input, the commitment to the circuit, and then what, you know, does the same exact thing. It's just the circuit is kind of getting into the verification through the commitment to the circuit instead of a full description of it. Okay, let's see time. 20 minutes. So yeah, this is good. I'll get through basically the rollups, and you still won't know how SNARKs work in any detail, and then if Tim lets me, I can tell you some more detail next time. Okay, so that's front end. So let's talk about back ends, and this is really what I know more about, to be honest. But you know, they're both really important for end-to-end costs, so I need to talk about front ends. So just a very brief summary, a high level of what various projects are doing. So Starkware's back end uses the Fry polynomial commitment scheme combined with, you know, some constant round polynomial IOP, which I won't get into the details of at all. And so Fry, if you remember from last time, it's the polynomial commitment scheme that's with the shortest proofs among plausibly post-quantum polynomial commitment schemes. And the proof length is like log squared of the size of the polynomial being committed, like times the security parameter. So they're still big-ish. You know, we could hope to do better in the future, maybe. Certainly compared to KZG polynomial commitments, which are used in Planck. They're not post-quantum, and they require a trusted setup. So that's what ZK Sync is using, is just Planck. So that is a constant round polynomial IOP combined with KZG polynomial commitments instead of Fry. It's a different polynomial IOP underlying it too. There's a project called Polygon 0, which is using Planck, but they want post-quantum security, and they also like Fry for other technical reasons, I think. So they're just kind of swap out KZG with Fry. So Zcash is now swapped out KZG with bulletproofs. None of the rollups will do that because bulletproof's verifier is not work-saving. So the proofs are short, but the verifier has a long runtime, so you wouldn't want that to happen on chain. So I thought I'd mention that as like an alternative, but that's not nice design choice for rollups. And kind of as I'll say a little more about soon, you know, I think that the prover computation in these SNARKs is going to increasingly be a problem. I would speculate that for these ZK EVM projects, just the circuits that come out might, you know, even after all the engineering, be pretty big, and it'll just, you know, the prover work to prove those circuits will just be challenging. This is pure speculation, but it just, you know, compiling solidity into circuits just seems like a challenging problem. So I know several projects are focusing on hardware acceleration for the prover, like I guess designing ASICs, like the actual hardware ASICs, for common operations done by these provers. Okay, so now I'll get into some more details of like the performance of some of these projects. So my main example is going to be Starkware. So they have kind of two products, if you will, called StarkNet and StarkX. I'll say more in a second about them. My goal is just to give a sense of like the current latency, the current gas savings, the current throughput, and the current security features of the SNARKs, you know, that the most prominent projects are using now. So just some background on like what are StarkNet and StarkX. So StarkNet is a public smart contract L2. So I guess you can write, I think like smart contracts via Cairo, like arbitrary Cairo programs, and they can like interact with like any other smart contract deployed on StarkNet, I think. And then they're posting validity proofs of batches of StarkNet transactions to Ethereum. I think it's a pretty recent launch. It appears that there is only several $100,000 of total value locked in StarkNet right now. StarkX, in contrast, is permissioned and application specific, and there's much more. It's been running much longer. There's much more value sort of locked up in it right now. The main, I guess, client, if you will, is DYDX, which is a decentralized exchange. Although apparently they're leaving Ethereum soon, so I guess that will Starkware is Ethereum rollup, so that'll change. But anyway, so they the main so for what I'm going to describe, actually, you can forget DYDX. So there are several other StarkX users, and they turn out to be most relevant for the performance results I'm going to share with you, and that's because Starkware actually has StarkNet sharing a prover with these StarkX applications. And they call the shared prover Sharp, shared prover. And the prover is closed source, but the verifier runs as a smart contract on Ethereum, so you can see the verifier.
So when you say they share a prover, do you mean like it's the same software implementation, it's the same actual like server that's running it? Are they actually all in one big proof together?
Yeah, so as far as I know, they are in one big proof together, and the reason they can do this, well, the way it's architected so they can do this is because everything has to go through a Cairo program, and because it's a universal, they generate a universal circuit that can handle any Cairo program, they can just have, I guess, like one big circuit that I guess takes as input now, like, I don't know, 4 or 5 different programs, well, I guess 4 programs, and then the Cairo programs for each of the, I guess, the StarkNet contracts that are have transactions in there. In the batch. And then the whole batch is proved at once. And I think the reason they're doing this now is just to get the volume up enough to get gas savings, basically. So there's just not that much volume on StarkNet now. So it might not be enough to actually get major gas savings, but if they sort of combine batches with the higher volume StarkX clients, then you get enough to actually get gas savings, basically. Does that make sense? Okay. So, yeah, they, when I wasn't aware of the shared prover when I sort of started trying to figure out some performance numbers, so I thought I would just be able, like there was just a single StarkNet prover, and StarkNet has a nice block explorer, so I thought I'd be able to sort of just see everything going into the rollup and just have sort of unequivocal information on performance. But because of the shared prover and the StarkX is not some like public blockchain the way StarkNet is, I did email the Starkware folks, and they were very helpful in helping me understand the performance. So yeah, here are my findings. So as far as latency goes, so proofs appear to be taking 8 hours to generate. I don't know this for sure, but the minimum delay between a transaction hitting StarkNet and any proof getting verified on L1 is definitely 8 hours or more. So, and it can go up to like 16-ish hours. So what seems to be happening is they're waiting 8 hours for a batch to complete. And then they're computing the proof. And I mean, it's possible that they're computing the proof quickly and just not posting it until the next 8-hour window is up. But there's no reason to do that. So, I didn't ask them directly how long is your prover taking, but their answer was not inconsistent with the proofs taking 8 hours to generate. So anyway, what I can say with certainty is the latency for transactions is between 8 and 16 hours, and 8 of the hours are just waiting around for the batch to fill, but the rest is not waiting for the batch to fill. Okay. As far as what it costs to verify a proof, it's costing on average about 0.46 ETH. So this is from publicly, this is just me looking at a block explorer for Ethereum. Proofs take about 38 Ethereum transactions to verify. This is also consistent. I mean, I did this calculation myself, but there's sort of a nice website that just displays daily fees that the rollup services are paying on Ethereum. So this matched up to what they were reporting.
Do you remember what it is just in units of gas?
Units of gas.
This sort of depends on the
Yeah.
gas price.
Yeah. No, I should do that. So for ZK,
It was like millions, I assume,
yeah.
for verification.
Yeah, so I'm guessing, so I know Planck proofs are 510,000 gas. And my own estimates are that by using Fry, the proofs and the parameter settings that they're using, it's going to be about an order of magnitude bigger. But what the verifier does to check the proof is different. It's a bunch of hash evaluations instead of a bunch of elliptic curve operations. So I can't say that the gas costs, are exactly proportional to the proof size. Yeah.
It's also like somewhat an artifact of what's pre-compiled on Ethereum, right? Because Planck's getting like a huge performance boost from
BN256. Yeah, but Starkware is using KSAC 256, which is Ethereum's like built-in hash. So everyone obviously uses the primitives that Ethereum makes nicest to use. Yeah, but obviously whatever gas cost Ethereum set were somewhat arbitrary and not done with rollups in mind, and then they just have people just have to live with them. So okay, so yeah, like I said, Starkware was nice enough to send me, which I really appreciate, like transaction counts from like a week of StarkX clients, because they said there were APIs, which I never figured out. But so anyway, they made it simple for me. So yeah, based on those counts, there appear to be about 90,000 transactions in a batch, of which only a really small fraction are StarkNet transactions. So that sort of might explains certainly StarkNet users being interested in sharing a prover. And yeah, sort of, like Tim said, just talking about ETH per proof verification isn't so helpful. I should have looked at gas. But just sort of very unscientific estimate for the sort of gas savings they're getting, was about, I estimate about 100x, and this matches something that they said in a blog post. I don't know how old the blog post was, so seems like I was getting the right ballpark. Something to point out is just looking at gas costs. There's more costs that the rollup provider is sort of paying that are hidden because they're running the prover, which might be killing an Amazon cluster or something, right? So I don't know what those are. And then for the StarkX clients, I suspect, and they sort of mentioned it in the blog post announcing Cairo, that, that was my interpretation of their language, that an expert Cairo programmer might have, they have to write in Cairo so that they can all share the same smart contract, but you might have an expert Cairo programmer, for a StarkX client, and a StarkNet person is writing the Cairo program themselves. So, they talked about, optimizations that were being done in the Cairo program, and that's probably, I'm guessing, coming from an expert programmer. So those are sort of the caveats about this 100x number, and they claim, and I certainly believe them, 1,000x savings for DYDX and 20,000x for certain like mass NFT minting operations. I don't know the latency of these applications though. I think they mentioned for this 20,000x, I think the email said that these were like for 600,000 NFT minting operations, so that would be a much bigger batch than what, I think I was seeing 90,000 transactions in the Sharp batch, so 600,000 is at least 7 times more than that, and it's specific to the NFT minting. Anyway, so yeah, you get big enough batches and you can see like really amazing gas savings for sure. And the question is just how big can you get those batches?
So you're saying the verifiers that split between multiple transactions?
Yeah. Mm-hmm.
A very rough estimate is up like 7 million gas for that price right now. So it makes sense you have to split it in.
Yeah, and that would also make sense as I was just guesstimating the proofs are maybe order of magnitude bigger than Planck proofs, and Planck is 510,000 gas, so they're sort of matching up, but yeah. Yeah, so, fortunately, there were, blog posts and, stuff they provided to me in email, and what the performance I was sort of guesstimating through extremely unscientific means is fortunately like matching up with them. So, yeah, like even though my methods are not great, there doesn't seem to be any kind of mystery or disagreement here or anything. So let's talk about security. So Sharp claims it's running its SNARK at 80 bits of security. So what I mean is the smart contract won't let it run at lower than 80 bits of security. And I looked on chain at like what the parameters are, and it's running at 80 bits of security. But one thing I sort of want to clarify here is it's actually running Fry, which is the polynomial commitment it's using, at 48 bits of security, and that's under what I consider pretty aggressive conjectures about its soundness. So it's basically asserting a specific, fairly simple attack is optimal. So the proved security, like what we can formally analyze of Fry is at most 22 bits. So how are they going to 80 bits of security if they're claiming 48 bits from Fry? So they add a 32-bit proof of work puzzle that basically, so what's kind of happening is for the prover in its own head to kind of attempt to find a convincing proof of a false statement with probability 2 to the minus 48, it has to first solve a 32-bit proof of work puzzle. Okay, so they call this grinding. Okay, what this means though is that, sorry, this is a little technical, I guess you can just jump to like this bulletproof here. So with more or less 2 to the 64 hash evaluations, you can have a 2 to the minus 16 chance of finding a convincing proof of a false statement. And if you up that number of hash evaluations to 2 to the 80, you can get that probability like quite close to 1. So this is like an attack that is there even if the conjectures are true. Okay.
Can you say something about the conjectures for 48 versus for 22?
Yeah, so, I mean, shortly, it's, we just don't have, there's a gap between like the attacks we know on like what a cheating prover can, with what probability convince the verifier to accept, and with what obviously we can analyze. And there's certain technical lemmas that go into the analysis. So one part of the conjecture is that like this technical lemma, so all of this involves Reed-Solomon codes, and the technical lemma is proved up to what's called the Johnson bound, which is some kind of list decoding radius for Reed-Solomon codes, and so that turns out to be like 1 minus square root the rate of the code. So one part of the conjecture is that like the same result would apply all the way up to you can get rid of the square root over that rate. And that conjecture alone is not enough because the way they analyze like the combination of the Fry security analysis with the polynomial IOP involves list decoding. And so the Johnson bound, which is a list decoding bound, comes in again. So you then, I guess, need even more, like a second part of the conjecture that says like not only can the technical lemma analyzing Fry like go up past the list decoding bound, but you also have to conjecture there's like another way sort of around needing list decoding, or I don't know enough about list decoding. Maybe I don't know if you could just conjecture that there are better list decoding results out there. I have no idea really. But this list decoding bound is coming up in terms of so the prover is claiming to like have sent like a Merkle hash, that of like the leaves are evaluations of some polynomial, but the verifier doesn't actually know like is this a polynomial. So the question is like how far away from a polynomial is the actual thing that's committed, and that's where the Johnson bound is coming in. Is that helpful?
And what about the 22 bits of security is proved under what?
That is proved in an information theoretic statistical sense, and the crypto is only coming in terms of Merkle hashing with collision-resistant hash function, and then applying Fiat-Shamir to cut out the interaction. Yeah, so 22 bits refers to the statistical security of the interactive thing that then gets sort of Merkle hashed in. Okay, so here's my really half-baked analysis though of these attacks. So I think they might eventually make economic sense. I mean, they certainly don't today, but I looked up, apparently, several years ago, 2 to the 64 SHA-1 evaluations cost about $1 million. And in principle, the way people think about these rollups is if you can produce a convincing proof of a false statement, you can potentially steal everything in the rollup. I mean, could you in practice? I don't know. People will, and can you actually spend all those funds? Probably not. But the idea is that the SNARKs are just going to protect you completely, and all bets are off if someone finds a convincing SNARK proof of a false statement. So, the hash function they're using is not SHA-1, it's some variant of SHA-3 because that's what's built into Ethereum. I think that's only a factor of, 3 or something slower. So you could imagine running this attack, you pay $1 million or something, and, if you succeed with probability as 2 to the minus 16, you get, I don't know, 100, everything in the L2. If they actually gain traction, could be $100 billion, right? In principle, I don't actually think you could spend that money. And the expected winnings are significant. You would come out ahead in expectation. It's just, not a great probability you're going to succeed, but if you do, you win so much money. And if these rollups, some of them might launch a token. I mean, Starkware hasn't announced plans for that, but ZK Sync is going to for their off-chain incentives, data availability. And in that setting, you could definitely, an attacker could make money without being able to spend stolen funds, right? You just ruin the rollup, the token is worthless. If you shorted the token, that's how you can make your money. And you could potentially find other ways to short companies if they don't have a token. So yeah, I mean, right now, attacking, running the sort of trivial attack on this kind of SNARK doesn't make sense. But in a world where rollups are highly successful, it might. Okay.
Now only the group of provers can make a proof, right? Who can add a SNARK proof over there?
Yeah. So in practice right now. I think the answer is only Starkware because StarkNet prover is shared with StarkX, and I don't believe that the data underlying StarkX is available publicly. That's my best understanding. But if StarkNet, it's new. It's every time I check on it, the total value locked in it is going up. That'll be a public blockchain. All of its data should just be sort of publicly available. I didn't see anything in these, kind of sharp verifier smart contract that required a digital signature from Starkware. If you look at their way of thinking and their plans and blog posts they described, it wasn't clear to me. They talked about, well, what if the rollup provider gets, so in the context of the data availability discussion we had before, they were worried about the rollup provider getting compromised, which suggested to me that they were imagining only the rollup, you only had to worry about the rollup provider doing this data unavailability attack situation. But if the smart contract, if the data underlying the state of the world is public and the smart contract doesn't require a signature, then anyone can submit proofs. So I don't have a complete firm answer to your question. Okay, so let's discuss why why they would run at 80 bits of security. So in a sentence, it's to save gas. So what they're doing, they could increase the security without meaningfully affecting the prover time. It would only slow down the verifier that's running on chain. So they're doing this to save gas. Okay, so some takeaways here. So the existing post-quantum SNARKs, they all have bigger proofs than the shortest non-post-quantum SNARKs. And in particular, those proofs grow linearly with the security parameter. So this is why StarkWare is sort of setting that security parameter aggressively in small. Yeah, and I think I already mentioned that. My rough estimate is at the parameter settings they're using, their proof should be about 10x bigger, roughly 8 to 10, something like that. So there's this notion that post-quantum security is better, future-proof. It's kind of part of the branding of the post-quantum rollups. But if your classical security is substantially worse, possibly to the point of making attacks make economic sense now, is it really better? Especially while the L1 itself is using non-post-quantum secure crypto and all this stuff. So that's something to consider. Also, while I don't know that the prover is taking 8 hours to run for sure, it sort of appears to be unless they're just sitting on the proofs. So I think that the latency will continue to be a concern moving forward as batches get bigger and people maybe start doing more than just doing swaps and minting NFTs if that ever happens. Something to point out is SNARKs with slightly bigger proofs might be fine if the prover is significantly faster, because then you can take the batch sizes to be bigger, and like a bigger proof from a bigger batch might actually be better than a smaller proof from a smaller batch. So this is sort of where I'm hoping to make some headway with the composed SNARKs I was mentioned last talk. Okay, and then I know I'm out of time, so I have an ultra brief case study for ZK Sync, and then like one wrap-up slide, and then that's it. Okay, so just to compare, because ZK Sync is using Planck, it's not post-quantum, it's not transparent, so just to compare performance. They have a block explorer. They actually post timestamps when the commitment to the new state of the world is posted to the L1, and they also post timestamps when the proof gets verified. So looking at their block explorer, the proofs typically capture several thousand transactions, so much less, by at least in order of magnitude, than these sharp, StarkNet and StarkX batches. And the latency tends to be several hours, but this appears to mostly just be waiting around for batches to fill, because I wasn't able to get a sense on my own of how long the proofs take to compute, but ZK Sync's documentation says it should be about 10 minutes, so I don't have any verification of that, but yeah, this was just an example of what you can see on the block explorer. So all of these things have been committed, but not to L1, but the proof hasn't been posted. Whereas all of these, it says verified here, the proof has been posted and verified.
And would you say that relatively fast proof time is driven mostly by the limited set of operations, or is the fact that these different SNARK also
it's very hard to know. I mean, in general, I would expect for a given circuit size, the StarkWare prover should be Fry bottlenecked for the prover time. But I would also suspect, because they're using the CPU abstraction, that their circuits are pretty big. But this is just based on just high level, they're doing this CPU abstraction. Here, the circuits are highly hand optimized. And the prover should more or less be KZG bottlenecked, but also has to maybe commit to more. I don't know the comparison of how many polynomials are getting committed in each, and that's also going to really affect the prover time. Because Planck requires the prover to commit to a large number of polynomials. And yes, StarkWare's polynomial IOP probably does too, but I don't know the exact comparison. So yeah, there's a lot of components to these SNARKs. So to actually isolate bottleneck costs, you really have to sit down and look at the circuit, look at the underlying polynomial IOP, look at what the polynomial commitment scheme is. I think for a given polynomial, like one polynomial of a given size, how long does it take KZG to commit to it? How long does it take Fry to commit to it? I think KZG should be a little faster. So, yeah.
Circuits here are a lot smaller, right? Because they only do a payment operation. That's all it supports.
Yeah. So I would guess the circuits are smaller, the batch sizes are smaller by a lot, and this is getting a little more speculative, but I would think that the prover for a given circuit size is also probably a little faster with Planck than with anything using Fry. And so they all sort of combine to, give apparently about 10 minutes, versus possibly 8 hours, although again, I can't say that with certainty. Should have just emailed them and said, how long is the prover taking instead? Yeah, is that helpful? Okay, so just the last thought for today. With the case studies and this discussion of security and latency and stuff, I hopefully made clear that I do think that these front end and back end like SNARK choices have major implications for performance and security of the rollups. Another thing I realized, I was trying to just understand what these rollups are doing. Like there's a lot more that goes into them. Just designing the whole system and the community. I think like the block explorer for StarkNet was just contributed by a community member. These smart contracts on StarkNet are probably going to interact with each other. So, there's a lot of success of the rollups are going to depend on a lot more than the thing that I know about. But when security is important and latency and throughput are important, so you should understand these details that I tried to kind of cover today, but there's a lot more too. And so the more I look into these rollups, just the deeper sort of the rabbit hole goes of everything you have to consider as you design or build them.
I mean, I will say that whole list is relevant for almost any project. Yeah. And so what's really cool here is that in addition, like how well you can implement these core primitives through science also really matters.
I agree, yeah. So maybe for most projects it's everything but this, and here's the
core engineering challenges are usually hard and interesting.
Mm-hmm.
Right?
Yeah.
Do you know, aside from Starkware, which I guess much have their patents, but they have like some closed source stuff.
Yeah.
I think most of these other projects are open sourcing everything, and so I guess like I wonder how much, even if they develop like a really fast prover, like it can sort of be adapted by anybody else, right?
Yeah, it's not clear. And then with hardware acceleration for the prover, it's a whole nother story because so some of these projects like actively want to distribute the prover both for liveness reasons, and other reasons too, I guess. But if you're imagining running the prover on an ASIC, because that's what it takes, you need all these people out there to own these ASICs.
I guess I'm wondering about like from a business perspective, like what's the barrier to entry for any of these rollups if the market kind of settles on like a specific proof backend and front end that everybody likes, then it could be like portable for somebody else launching their own competing rollup. Maybe hardware is like something that's actually like could be like a barrier.
So potentially the hardware.
It's a centralized bottleneck, right? If they're the ones rolling up the proofs, they have to run the proof as well. And people have to trust that they stay online forever.
Yeah, I don't know. You could imagine a world, I guess, where there's a centralized roll-up with the best performance, but no one else can use it. And so, but if they start censoring you, you can go to a less performant roll-up. Just speculating, I don't know. And there is this difference in open sourcing stuff. I know ZK Sync 1.0, for example, is all open source, and I don't know if Starkware eventually plans to open source some of these provers, but they open sourced a prover for like a toy computation, like a hash chain verification, apparently, but that doesn't support general Cairo programs, so you certainly can't use it to prove StarkNet rollups, even if it wasn't shared with StarkX. So I don't know what the plan is there.
There's another open source project that tries to optimize the prover system.
Yeah, a lot of the projects are open source. Polygon Zero is open source. I do wish having gone through this exercise of trying to figure out what a lot of these projects are doing, I wish there was more than just the source code, because it can be hard. Sometimes you have to go to the source code for some of them to know what's going on, and that's not a fun process. But it's definitely appreciated that there's a ground truth to what they're doing because the implementation is there. Okay, so that's a good stopping point for today, and maybe next time we'll actually see what these SNARKs are doing after 3 hours of listening to me. So.
Thanks a lot, Justin.
Yeah, thanks.